So something like this, let's say we're trying to figure out the most likely fragmentation. So the first thing that's going to happen is it's going to go into the electron beam, and one electron is going to get knocked out. But since we don't have lone pairs here, we don't know exactly where that's going to be at. So we put a dot plus. So essentially the whole thing is in brackets. All right, we know one electron got ejected, but we just don't know where in the molecule. And then from this point, we got to decide where best to break it up. And actually, so this is quiz 2, 2014. And it's number 2. And actually, I don't like my answer. I'm going to change my answer. If I number my carbons, 1, 2, 3, 4, 5, 6, and 7. I think the best bond to break, the most likely fragmentation will be there. So break between C2 and C5. And one of those carbons is going to be a radical, a neutral radical. One's going to be the positive fragment. Which carbon do you want to make the positive fragment? The two, number 2. So like that, the tertiary, right? 1, 2, 3, 4, plus neutral radical, 5, 6, 7. So that'd be the most likely fragmentation. One I had isn't as good. If you broke one of these off, I mean, there could be an argument made that there's more of those, so it's more likely to break. But this would give, if I broke here, I'd also have a tertiary carbocation, right? If I did blue, let's say broke there, I would have a tertiary carbocation, but then I'd also have a methyl radical, which wouldn't be good at all.
Could we do the
7, so it'd be a plus charge, and there'd be a CH3 with a dot, 3, right? So I would say this would be worse because a methyl radical is way worse than a secondary radical. So here, asking for the least likely fragmentation, there's a couple options I guess I would go with. The one I put for an answer for here, I said breaking here because it gives both a primary radical and a primary carbocation. You also could have thought maybe here to give maybe a secondary carbocation and a methyl radical. I think the primary is probably the better answer, but both would probably have been fine in this case. Versus over here would have been if I did the blue. And a CH3 dot, which I would guess would be the worst. Right, 5, 9, 6, 7, 8. I like this answer better, but you can. Primary. Methyl is bad too, but whatever. Okay. At some point, if you're worried about that stuff, then I didn't write a very good question. Right. So again, here asking, this is exam 2, 2014, number 2. What are the structures of 3 major fragments we'd see? So again, what you want to do here is you want to essentially have the most stable carbocation you can. It's all about stabilizing the carbocation. So the best way to stabilize a carbocation, if you have a pi bond around, is to have that carbocation be next to that pi bond. Right? So have it be able to do pi bond resonance. So if I break this bond, right? If I had a radical, right? Molecular ion. If I broke there, I would have a CH3 dot, which isn't great, but I'd have a carbocation that can do resonance, right, with this pi bond, right? It can do resonance with that pi bond. It's going to stabilize that fragment a lot. So what other bonds would you break? You could break here, same deal. So potentially you want to get a plus charge on this carbon because that's the carbon that's adjacent to that carbocation. So you break here, or break here. That'd be the best 3 spots. You could also break here and get a tertiary carbocation too. That's good, or here. But I would say the 3 spots with the allylic carbocation would be the best, right? You're always trying to stabilize the carbocation as best as possible.
So even though you have the methyl radical,
even though I have the methyl radical, this stabilization is so much better. Like actually being able to spread the charge out is so much better than hyperconjugation, right? lone pair resonance, right, the three ways. We have lone pair resonance, pi bond, and then hyperconjugation. Right? Lone pair and pi bond actually move electrons. That's going to be a lot more stabilizing. They're actually resonance, right? Pi bond resonance, pi bond resonance, lone pair resonance. Hyperconjugation doesn't actually move electrons, so it's nowhere near as stabilizing. So if you can do lone pair or pi bond, that's going to be way, way more important. That'd be really more stabilizing. So try to do that.
More stable out of the two or?
Lone pair,
Okay.
octet rule. Yep, 1, 2, 3. And it's like 1, 2, and then like way, way, way down third place. So benzene ring substitution. Benzenes have 6 positions, right? Monosubstituted would have how many aromatic hydrogens? It would have 1, 2, 3, 4, 5, right? And depending, right, and with monosubstituted, these would be the same as would HB. We did a lot of this in lab, right? So those would be there. We could also have disubstituted benzene rings. Now it depends on what we have here, whether or not these are the same or different. But how many hydrogens would be in a disubstituted benzene ring? 4. And it could be a 1,4 pattern. So you could start to recognize, right, this would be, whatever these are, and these are, they'd be doublet of doublets. Right? Here's another disubstituted pattern. You could have one here by itself, which would be a singlet. These other two would be the same if these are the same, right? And they'd be coupled here, right? So you could start to see, again, there's 3 ways to do disubstituted. 1,4, 1,3, and 1,2. Right? And it depends on what's on these substituents, what the splitting and things like that will be here. You could also do trisubstituted. Right, so when it's trisubstituted, how many aromatic hydrogens will there be? 3. And depending on how, right, you'd have to know whatever these two are, whatever this is going to be coupled to this, right? So there'll be some information you'll know. What's another way it could be trisubstituted?
Like one of the high bond, or the.
This way and this way, right? Then, right, these two would be coupled, but this would be a singlet. Another way you could do it is like this. Now these would all be, right, not coupled to each other. They could, I mean, it depends on what's here, right? If this was the same here, if these two things were the same, then this would be the same and these would be the same, right? There's different ways you could do that, but you could start to map out possibilities and see what would be split with what. Right? Then even tetrasubstituted. Right? There's one way. Could do it this way. You could do them all 4 next to each other. Right? So really you gotta look at how many aromatic hydrogens there are. How many hydrogens in the aromatic region from 6.5 to 8.5. And that automatically, once you know if there's only 4, right, then it automatically narrows it down to 1, 2, 3 possibilities. If you know there's only 3, it narrows it down to 1, 2, 3 possibilities, right? So it's not, don't overthink that. Yeah. Right? The number of hydrogens gives it away. It has to be only so many patterns. Then you can look at the coupling constants. Who's coupled to what? And then it all should make sense. Okay, got a problem here. C7H12Cl2.
Are we always given the IR values?
Not always. This case, this problem, you're not given anything for the IR. So if it's necessary, you probably will, right? C7H12Cl2, degrees of saturation is 1, right? Biggest thing here is X is chlorines and X. Chlorine's a halogen. So you remember to use that part of the equation. You have 3 peaks. So I would again think, right, maybe symmetry, especially because can one carbon have 9 hydrogens bonded to it? No. So there must be some sort of, right? If I see 9 H's in a singlet, I'm thinking there's 3 CH3s bonded to a carbon, right? That has no hydrogens bonded to it, right? So let's just do that. Let's start with that then. Let's start with that piece right off the bat for A. So A, we're going to say it's 3 CH3s. Good. Let's subtract that from our formula. So we can cross off A. So it's what? It would be minus C3, what? Not H9? All right. C4, H3, Cl2. Good. We have B and C. B and C here. What do you know about B and C? They're coupled to each other, right? These guys are coupled. So you can write coupled, C, coupled. So B is 2 H's. So that's going to be probably a carbon with 2 H's. That'd be the best guess. B, B. And on one side of that carbon is there must be the carbon that has HB must be attached to the carbon that has HC. Right? But now, if we take a step back here, something's weird. Because we haven't done yet, we have 2 empty spots. We have a degree of unsaturation we haven't used yet, right? So maybe I take a step back and look and say, well, wait a second. Now let's look at the frequencies, right? So you got your pieces now. And you're going to take a step back and say, something's up with these frequencies. Let's subtract this out first, actually. Let's do that. So minus C2, H3, we have C2H, Cl2. No H's.
Yeah.
Oh, my bad. Math is tough. There you go. So we have C2 and Cl2. So now we're kind of stuck, right? We're kind of stuck. I can draw this right here. I know the Cl's, right? How many bonds does chlorine make? 1. So I know there's Cl's like that. And then there has to be some carbons. Yeah. Right, so there must be some carbons. This tells me there's carbons that don't have any hydrogens bonded to them. Yeah, so we're getting close. So these carbons have no hydrogen bonded to them. I have 2 chlorines. Now I go back and look at the frequencies and say, wait a second. 5.77, that's high. What area is that in? That's probably vanillic. This C right here might be, it should be, right? This HC, this carbon here has 2 open spots. I'm thinking those 2 open spots are probably 2 bonds going to the same carbon. This carbon must be a vinyl carbon because this is so high. So I'm going to redraw this piece, reimagine it here. What if it's this? There's HC, and then it's double bonded to something else. All right, so I'm going to cross this out for right now. Now this looks a little better, right? I don't know what's on, I'm guessing there's a carbon over here. And do we know what's on this carbon? We don't know yet for sure. What else could it be? So it could be, so what do we have left for our pieces? We have 3 CLs, we have 3 CH3s, 2 CLs. We used one of our carbons, right? So this is one of our carbons. We should, don't forget our subtracting. So we lost the 2 CLs. So those are gone. And I've added a carbon here. So I lost 1 carbon. So what do we have left? We have left is a carbon by itself. So let me circle our pieces. A CH3, a CH3, a CH3, a carbon by itself, 2 chlorines, and then this piece. The hard part here was taking a step back and recognizing that this HC was way too high, that this carbon had to be double bonded to another carbon. That was the tough part right here. Right, that was the tough part. But we didn't get to that until we went back and looked at our frequencies. So now see if you can put the rest of this together. So the final product here, which that is not part of, it will look like this. The chlorines are actually off the other end. And the reason I knew that was because the chlorines couldn't be next to this position. These were H what? HB?
Yep.
What was the frequency for HB?
242.
Right, so I can't get the chlorines anywhere near these. Right, if the chlorines were on this other side, or if I put a chlorine over here, these would have been much more farther downfield and that wouldn't have worked. Right? So when you get to the point of the test, you start putting things together and you go back and check. Right? And if you're short on time and you've checked and you know this isn't right, I know this isn't right and here's why. If you don't, right, but if you write here, I don't think this is right and you get it right, then that's not good. But if you go back and check, right, and say, I'm out of time, but I've checked this and I know it's wrong for this reason. But don't just say it's wrong. Give me a reason. Give me a reason to give you points to say that you went back and checked and you realize why it's not there. Right? So don't just say I think it's wrong. Say I think it's wrong because, and make sure that reason's legit. Don't just like say something. Right? So let's do some alpha cleavages. So let's pretend the electron got ejected from our alkyl halide here. So electron got kicked out. I'm gonna draw this molecular ion twice. All right, so the first one I'm going to do, from here I'm going to do let's do a good old-fashioned alpha cleavage. And let's do it from the more stable side, right? So which side would I rather do it from? So if I number these 1, 2, 3, 4, the more stable products would come from making the radical on 4 or 2?
2.
2, so let's do it that way. All right, draw there. Electron from the chlorine, one of them. Electron from the bond, one of them. Electron goes to the carbon. So we broke the bond between the carbon 2 and the carbon bond to chlorine. So the product, a radical there, 1, 2, 3, plus the positively charged fragment, which is now the chlorine fragment. Right there. There's 4. And then, of course, our plus charge. And that's the fragment we'll see. So that'd be the most stable alpha cleavage, to have the more substituted radical versus a CH3 radical, methyl radical. So this was the more stable fragmentation because either I have a choice. I can break this bond or this bond for this alpha homolytic cleavage. If I break this bond, I put a radical on carbon 2, which is a secondary carbon, which would have 6 hyperconjugation buddies, right? Because radicals are electron deficient. Radicals do not have full octets. Or I could break this bond and have a CH3 dot, which would be a methyl radical, which would have 0 hyperconjugation buddies. Right? So that'd be much less stable, less likely to happen. Okay. Another molecular ion is drawn in again. This time I'm going to do a heterolytic cleavage. In this case, 2 electrons just go right to the chlorine and that bond breaks. So that fragmentation now would create a carbocation, a secondary carbocation, right, which has 3 hyperconjugation buddies there, 1, 2, 3 hyperconjugation buddies there, so 6 hyperconjugation buddies, so it's secondary carbocation. And then we always make a positive fragment, and then the other thing we make is a neutral radical, which would just be a chlorine with 7 valence electrons.
If the chlorine did not have 7, then would the plus go on the chlorine?
Right. But remember, chlorine starts with 7 valence electrons. Sorry. And then you look at this arrow, right? Who's losing electrons? It's that carbon, so that's why it would have a plus charge. So hyperconjugation. Hyperconjugation is when you have a carbocation, right? It's the least stabilizing form of stabilizing a carbocation. It's sigma bonds 2 bonds away. So sigma bonds 2 bonds from the carbocation. Alright? So that would be these H's, or if I had a methyl here, that'd be 1. Alright, so in this case I have 1, 2, 3, 4, 5, 6, right? 1, 2 bonds away. I have 6 hyperconjugation buddies. What does that look like in a molecular orbital picture? Which you should be able to draw. Carbocations are sp2 hybridized. So they have an empty p orbital. In this case, there's an H here. This is not drawn in. And something going away, coming out. Your hyperconjugation buddies are out here. Now this carbon is sp3 hybridized. So what's the bond angles for this carbon? 109.5. So it's not lining up perfect because this is, right? This is 90 degrees there, right? So they're not lined up perfectly here. But they're close enough to like kind of help. These 2 electrons in this bond can kind of help. And these 2, like, as it rotates, it can kind of help. As can these as well. They're coming out. Right? It's not perfect. It's not a perfect orbital overlap. Right? It's kind of skewed at an angle. But as this bond rotates, right? As this bond rotates, these 3 bonds, sigma bonds, 2 bonds away, can help stabilize this empty p orbital. Because this is empty. There's no electrons there. But there's electrons in these bonds. So they're kind of close. It's not a perfect orbital overlap, but they're kind of close. So sigma bonds, 2 bonds away, can help stabilize this empty p orbital. That's hyperconjugation. So the more you have, the better.
And it only works with carbo.
It's for carbocations. It's for carbocations. Yep. So yes, a tertiary would have a carbon here with 3 sigma bonds. That'd be better. Primary wouldn't have 1 away 3, and then a methyl would have H, H, and H. So a methyl would have nothing 2 bonds away. So it'd be the least stable.